All right, so now we continue on to lesson 3 of polynomials, and this is going to start to seem really familiar to our exponents unit, or unit number 2. We're going to multiply and divide polynomials using the rules that we learned in exponents, or the rules of exponents. So just as a quick reminder, well, we want to discuss the multiplication rule or product rule, division rule or quotient rule, power rule, and then zero and negative exponents. Remember, if we're doing multiplication rule or the product rule, we're multiplying two common bases where we keep the common base and then add their exponents. If I do the division rule, well, the division rule is also known as the quotient rule, and it's if I have one base divided by another that are common, I keep that common base and subtract the exponents. By power rule, we know that if we have some base raised to some power, then we're going to multiply their exponents. Finally, last couple things here, we have a over b written as a fractional power rule. We know that this power distributes to both a and b. And then if I have a zero exponent, or the case below here, anything raised to a zero power is 1. Finally, an a to the negative x, that's just the reciprocal of whatever the base is. So I could also write it as such. What if I had instead 1 over a to the negative x? Well, what would I do? In this case, the negative means I take it from the denominator and move it to the numerator. And so I would have the reverse case of what I have in the above there. All right, so let's consider some examples just to make sure we understand what's happening in each rule. So in the first one, we have product rule. A base times a base, we add their exponents. 3 plus 4 equals m7. If I have the quotient rule or the divisional rule, it's a common base over another common base. I subtract their exponents. 9 minus 2 is 7. Now, if I have the power rule, xm times n, we know a base raised to 2 exponents like this will be the multiplication by power rule. And we could also say that if I had more than one base in the brackets, the c, or whatever power is out front here, would distribute to both a and b. So therefore, you would get something that looks as follows. And the same thing works with divisional terms. They also get the distribution by power rule, and we know this from our exponents unit. And so they use a couple examples below. Well, they go m cubed times the 4 on the outside. This will combine to make 12. We have the second case where we need to distribute. The 5 will get multiplied to the 3 and 4, making 15 and 20. And then finally, we know here we have a 3 here, a 4 here. By our exponent rules, this is a power rule for both the numerator and denominator. So 3 times 5 gives us 15, 4 times 5 gives us 20. Okay, after that brush up of those, now we want to go on to multiplying monomials here. When we multiply monomials, essentially what we're doing is we're saying if they have coefficients, we want to make sure we multiply those coefficients together, and then we want to follow standard power rules with the rest. So let's actually try an example because I think it's going to be best to see it. And this is very, very connected to our exponents unit. So right away, we think about order of operations. I want to use bedmass. So if you need to write this down again, I would definitely do the following. Write out bedmass because we know we have to follow order of operations anytime it comes to not only anything in math, but just the exponents rules as well. So our first thing is the brackets or the b. Brackets, we have to look at and see, is there anything we can simplify on the interior here or the interior here? In this case, no, they're already simplified. So now we go to our next piece, exponents. I need to take both exponents, 3 and 2, and figure out what I do with these. So from exponents, we knew that they get distributed in where 3 has a 1 and 2 has a 1 in the exponent. And by distribution, I go 3 times 1, 3 times 3. This will give me 3 to the third power. X to the 3 times 3 is 9. Times, we keep this in brackets. I have 2 to the 2 times 1 is 2. X to the 2 times 2 is 4. All right, now I want to simplify those numbers here. We have 3 to the 3, which is 27, x9, times 2 squared is 4, x4. And now I can multiply these by product rule. 27 times 4, that's going to give me a total of, we'll have 108. And then by product rule, or the x times x, we keep the common base and add the 9 plus 4, which gives us 13. So our final solution is 108x13. All right, let's go to our next example here. Yet again, we're thinking, can we simplify anything on the interior here or anything on the interior of this brackets? No, now we move on to our exponents, or the second piece of BEDMAS here. I'm going to distribute this 3 to both, or all 3 of these, I should say, where b has an exponent of 1. So if I rewrite this out, I have negative 4a squared b3. There was no exponent to distribute there. Times, this is 2 to the third power. A to the negative 1 times 3 is negative 3. Finally, b 1 times 3 is 3. Now, I could flip this negative exponent here. I could say, yeah, we know negatives will flip to the denominator, so I could make this 2 to the third power b3 over a3. However, I'm not going to do that. What I'm going to do is instead, not that you would be wrong by doing that, I'm going to just use product rule here. We have negative 4 times 2 cubed. 2 cubed is actually equal to 8. So we know this is equal to 8. Therefore, I can say 8 times 4 will give me negative 32. I keep the common base of a and go a squared times an a negative 3 is 2 minus 3. That's negative 1. And then finally, b3 times a b3, that's 3 plus 3, or 6. So this is equal to negative 32, b to the 6, all over a to the positive 1. We flip that negative exponent because we never want to leave things in terms of a negative exponent. We bring it to the denominator and make it positive, giving us this final answer here. So we're still following BEDMAS. We still want to follow our typical exponential rules from our last unit exponents. Now we're just piecing it together in terms of polynomials, or multiple monomials coming together. All right. Whoops, we got to go back and do this example here. We're going to apply this one here. So we look to the inner brackets and we want to see, can we simplify anything on the interior? It doesn't look like it. So now we go, let's see if we can multiply all the coefficients together. And I'm actually going to show you a way to organize this. Just as we've done previously with adding and subtracting, I could go, I have a coefficient here, here, and here. I have a c here, here, and here. And finally, I have a d here, here, and here. By doing this organizational strategy, now I can go, well, negative 8 times 2 is negative 16. Negative 16 times a negative half. A negative and a negative become positive, and 1/2 times 16 is 8. Now, I keep my common base and I say C3, C1, and C4. That's going to add up to be C, positive 8. I have D, which is the common base, D2, 3, and 1. This is going to add up to 2 plus 1 plus 3. That's equal to 6. And there's our final solution there. So there's a couple ways to do these, but you want to realize that organization is really important, and that when you're doing simple multiplication like this, we're just going to follow the product rule that we did from exponentials, or the exponent unit. All right, now dividing monomials. So if we're looking at dividing monomials, well, just as we did with multiplication, we just multiply the coefficients and we use product rule on the exponents. Now we're going to use quotient rule and standard division. So if I look at the first problem here, well, 20 over 60, this can actually reduce to equal to x squared over 20 divided by negative 60. They both divide by 20. Therefore, I have 1 over negative 3x. And now by quotient rule, I can look at the x squared and the x, and I can combine these and say, well, by quotient rule, we subtract the exponents. I have an x2 minus the 1 from here. This is going to be equal to x over negative 3. And I could put this 1 out in front if I really wanted to, but 1 times anything will just give it itself. Now, I go to example 2 here. I need to realize that if there's any exponent outside of the entire function, like here, or outside of the entire monomial, I have to apply that before I can compare it to the above. So let's deal with this exponent and distribute it to the brackets. I have a power of 1 here. Now in my next line, I'm going to just rewrite my numerator as 20x3y to the negative 4. And I want to put this over. In my denominator, if I have a negative raised to an even exponent, that's going to give me a negative times negative, or a positive number. Now I go 5 squared is 25. X negative 2 times a 2, that's x to the negative 4. And then finally, y2 squared, that's y2 times 2, which is 4. All right, if I go to my next line, now I'm doing standard quotient rule and dividing the numbers. 20 and 25 can both divide by 5. If I divide them both by 5, I'll get 4 in the numerator, 5 in the denominator. Now I can use my guess method or my approximation method and say, where are the x's greater and by how much? So where are they more positive? Well, definitely the numerator, because we have a positive x versus a negative x. It's greater in the numerator. By how much? The difference between 3 and negative 4 is x7. So we could actually find that our x goes in the numerator by how many? 7 units difference. Now, I can do the same thing with the y's. I can go y negative 4 over y4. We could do quotient rule or realize the y's are greater in the denominator. By how much? By a factor of 8. So your final solution should be 4x7 over 5y8. And that would be your final solution there. Now, just for the sake of it, I'm going to show the quotient rule off to the side. So by quotient rule, we knew this should be x3 minus that negative 4. That's equal to x7. And then we had y negative 4 minus, and I should remove that bracket, minus another 4. This is equal to y to the negative 8, or which is equal to 1 over y to the positive 8. So we should see that we had an x7 in the numerator like we did, and a y8 in the denominator, just as we have here. Perfect. All right, let's go to example 3. Example 3, we have multiplication in the numerator and then something divided. So let's deal with the numerator. I look and I say, can I simplify anything in the interior? Definitely not. Now, do I have any exponents to deal with? Not in either of these cases. So now I can go to standard multiplication and say 3 times 5 is 15. X squared times an x negative 1, that's 2 minus 1, or x to the positive 1. Y squared times a y1, that's y2 plus 1 is y3, all over negative 3xy. Now, just like I had in my numerator, I could put a 1 for both of these exponents if it's not listed, and now I'm doing standard division. This is equal to 15 divided by a negative 3 is negative 5. x1 over x1, that's x1 minus 1, or x0. We have y3 over y1, that's y3 minus 1, which is equal to y2. From exponents, we should know anything to the power of 0 is just 1. Therefore, our final solution is negative 5y squared. We don't need to move anything because we realize all our exponents are positive that we're left with. All right, now division of a polynomial by a monomial. So what if we had the above cases here, but instead we had multiple monomials in the numerator being added or subtracted, and then we divide it by a monomial? Well, if that's the case, in order to divide it, everything has to divide or nothing. I'm going to write that in a special note here. It's the all or nothing principle. All or nothing. Now, the reason I call it the all or nothing is because we have to literally divide everything in the numerator by everything in the denominator. And if that's not possible, we can't do this. So we look at 18. 18 is definitely divisible by 2. 10, is that divisible by 2? Yes. 6 divisible by 2? Yes. If it can be divisible by all 3, if I can put a check mark next to everything in the numerator being divisible, this works. And same with the variables. I have to look at the variables and say, is there an x on each term? If that's true, I can put a check mark next to each of these and say it's all or nothing. In this case, everything can divide, so we can divide this, and therefore you could divide each term. Now let's actually put this into practice. If I'm looking at the examples here, I have a 4t squared plus 8t over 4t. First of all, I want to check, is 4 divided by 4, or 4 divisible by 4? Yes. Is 8 divisible by 4? Yes as well. And now I need to check, do they all have a t on them? In this case, they all do have a t. So if you know you can pass all the checks here, and they're all divisible, well, 4 divided by 4 is 1. T squared divided by t is just t1, plus 8 divided by 4 is 2. T divided by t is t0. Therefore, this is equal to t plus 2. Because we know anything times 1 is just itself, and t0 reduces down to 1. So our final answer would be t plus 2. Let's do the same thing with the next example. I go, can 10 divide by 5? Yes. 5 divided by 5? Yes. 15 divided by 5? Yes. Is there an m on each term? There actually is. So we know that because there's m's on each term and they all divide by 5, we can do this. This is equal to 10 over 5, which is 2. M cubed over m1 is equal to m squared, plus 5 over 5 is 1. M2 over m1 is m1. And then finally, 15 over 5m, well, 15 divided by 5 is plus, in this case, 3. And m1 over m1 is m0. Therefore, this simplifies to 2m cubed, or m squared, I should say, m squared plus 1m, which we could just write as m, plus, we know anything raised to the power goes down to 1, and therefore that's 3 times 1, or just 3. So we've now had something that reduced down to a binomial. We had something that reduced to a trinomial. Now let's try one more example here. So if I have the example number 3 here, I need to check and see if all the coefficients are divisible. 6 divides by 3, yes. 3 divides by 3, yes. 9 divided by 3, yes. Do they all have an r? They do. This one has an r, this one has an r, and this one has an r. Now we can reduce them. 6 over 3 is equal to 2. R4 over R2, you subtract the exponents, leaving me with r squared. Negative 3 over 3 is negative 1. R3 over R2 subtracts to R1. And now we have 9 over 3, which is positive 3. R squared over R squared reduces down to R0. Just as our last examples, this reduces to 1. And now we have this is equal to 2R squared minus R plus 3 times 1, which is 3. Another one that reduces down to a trinomial. All right, this is where I want you to check your understanding of the lesson. It deals with a lot of exponential stuff or exponent stuff from the previous unit.